Let us begin not with excitement.com, but with honesty. I have spent my life working with equations. In 1924, when I proposed that matter itself carries a wavelength, that every particle, every electron hurtling through space is also a wave, the world thought I was a dreamer, a young nobleman playing at physics. But the mathematics did not lie. The Davisson-Germer experiment confirmed it 3 years later. The equations were right. They are always right, if you have the courage to follow them all the way to the end without flinching. Today I want to follow the equations of interstellar travel, all the way to the end. No flinching, no poetry, no Hollywood imagination, just the numbers. And what I will show you is this: the dream of sending human beings to the stars, the dream that fills your cinema screens and your magazine covers and your late-night conversations about humanity's destiny. That dream, as currently imagined, is a mathematical lie. I do not say this to crush wonder. I say it because wonder built on false foundations is not wonder at all. It is delusion, and I have no patience for delusion. Now, let us speak of distances first, because most people, even educated people, have no real sense of how far away the stars are. They hear 4 light years and they nod as if they understand. They do not. So let me give you something your body can feel. The fastest object humanity has ever constructed is the Voyager 1 spacecraft. We launched it in 1977. It is moving at approximately 17 kilometers per second, 17,000 meters every single second. That is faster than any bullet, faster than any jet, faster than almost anything you will ever encounter in your life. Voyager 1 has been flying for nearly 50 years without stopping, without slowing down, carried by the gravity assists of Jupiter and Saturn into the cold emptiness beyond our solar system. And where is it now? It has barely crossed the threshold of interstellar space. It is roughly 23 billion kilometers from the Sun. That sounds enormous. But the nearest star to us, Proxima Centauri, is approximately 40 trillion kilometers away. At the speed of Voyager 1, it would take roughly 73,000 years to reach it. 73,000 years. Not 73 years, not 700. 73,000. The entirety of recorded human civilization has existed for less than 10,000 years. We would need to launch a spacecraft today and wait for a period of time 7 times longer than all of human history just to reach our nearest neighbor. This is the first number you must sit with, not skip past. Sit with it. Now, I can already hear the objection forming in your mind. You are thinking, but surely if we travel faster, if we build a ship that moves at, say, 10% of the speed of light, the journey becomes manageable. And mathematically, yes, 10% of the speed of light would get us to Proxima Centauri in roughly 40 years, a human lifetime. That seems possible. That seems like something engineers could solve in a century or two. But this is where the mathematics becomes brutal. This is where the equations stop being our servants and start being our judges. There is an equation written down in 1903 by a Russian schoolteacher named Konstantin Tsiolkovsky that governs all rocket propulsion, everything, not just the rockets you see launching satellites, everything that moves by expelling mass. The equation is elegant and it is devastating. It tells you that the mass of fuel you need grows exponentially with the velocity you wish to achieve, not linearly, exponentially. You want to go twice as fast, you do not need twice the fuel. You need the fuel multiplied by itself in a way that rapidly becomes incomprehensible. Let me give you a concrete illustration. To launch a spacecraft from Earth into low orbit, you need roughly 9 times the mass of the rocket in fuel, 9 to 1. That is already an extraordinary engineering challenge, which is why rockets are mostly fuel tank and almost nothing else. Now let us ask what the Tsiolkovsky equation demands if we want to reach 10% of the speed of light, which is approximately 30,000 kilometers per second, using the best chemical propulsion we have, liquid hydrogen and liquid oxygen, with an exhaust velocity of about 4.5 kilometers per second. The mass ratio, the ratio of initial fuel mass to final spacecraft mass, comes out to a number so large that it has no physical meaning. The fuel required would exceed the estimated mass of our entire sun, for a single spacecraft. And this assumes perfect efficiency, no deceleration at the destination, no provision for the crew to survive, and no return journey. You begin to see the problem. But perhaps you are now thinking about nuclear propulsion. fusion rockets, antimatter engines, things that sound more impressive than burning hydrogen. And yes, these are more efficient. Nuclear fusion, if we could harness it for propulsion, which we still cannot do reliably on Earth, let alone in a spacecraft, might yield exhaust velocities perhaps 100 times better than chemical rockets. Even so, the calculations for a crewed mission to Proxima Centauri, traveling at a significant fraction of light speed, require fuel masses equivalent to tens of thousands of times the mass of our Sun. Antimatter engines are the most efficient theoretically conceivable propulsion system, and even they require fuel-to-payload ratios so extreme as to be practically impossible to manufacture, store, or handle. We currently produce antimatter in quantities measured in nanograms per year. A single gram of antimatter costs roughly $62 trillion to produce with our current technology. And yet science fiction presents this as a minor engineering detail, a solved problem, a background fact of the universe they have invented. Now I want to talk about something even more fundamental than fuel. I want to talk about what happens to matter and to human biology when you push it toward the speed of light. This is where my own work and the work of Einstein before me becomes directly relevant. When Einstein formulated special relativity in 1905, he revealed something startling. Mass is not fixed. As an object accelerates, its effective mass increases. At low speeds, the speeds of cars, planes, even our most ambitious rockets today, this effect is negligible. But as you approach the speed of light, mass increases without bound. To accelerate an object with mass to exactly the speed of light would require infinite energy, not a very large amount of energy, infinite. This is not an engineering limitation. It is not something we can solve with better materials or smarter design. It is written into the geometry of space-time itself. The equations do not say it is difficult. They say it is impossible. There is a difference. So we cannot reach the speed of light. We can only approach it. And even approaching it at 90%, say, introduces another phenomenon that your intuition cannot prepare you for. Time dilation. At 90% of the speed of light, time for the traveler passes more slowly relative to someone waiting on Earth. This sounds convenient. The traveler ages less, and in some narrow sense it is. But think through the implications carefully. If you travel to Proxima Centauri at 90% of the speed of light, from Earth's perspective, the journey takes about 4.5 years. The traveler experiences something less, perhaps a couple of years, but when you arrive, Earth has moved forward in time. When you return, assuming you could decelerate, turn around and accelerate back at the same enormous energy cost, everyone you knew has aged by nearly a decade. And this is for the nearest star. For a star 100 light years away, those who sent you would be long dead before you returned. Time dilation does not solve the problem of interstellar travel. It transforms it into a different kind of tragedy. And deceleration. I must speak about deceleration because it is systematically ignored in popular treatments of this subject. It is not enough to accelerate to high speed. You must also slow down when you arrive, or you pass through your destination in a fraction of a second and continue on into the void forever. Deceleration requires just as much energy as acceleration, which means every energy calculation I have given you must be doubled, at minimum, and then doubled again for the return journey if one is contemplated. What about wormholes? What about warp drives? I can see you reaching for them the way a drowning person reaches for anything that floats. These are the emergency exits that science fiction has installed into the human imagination, and I understand why they are popular. The mathematics of Einstein's general relativity does permit solutions to its equations that resemble wormholes, theoretical tunnels through space-time connecting distant points. They are called Einstein-Rosen bridges. They emerge from the mathematics of black holes. But there are several difficulties that cannot be wished away. First, traversable wormholes, wormholes stable enough for anything to pass through, require a substance called exotic matter with negative energy density. We have never observed exotic matter. We have indirect hints of negative energy effects at the quantum scale. The Casimir effect between very closely spaced metal plates, for instance, but the amounts involved are so vanishingly small as to be laughably insufficient for stabilizing a wormhole of macroscopic size. Second, even if exotic matter existed and could be gathered in sufficient quantity, there is no known mechanism by which one could create a wormhole, position its two ends at convenient locations, and keep it open while a spacecraft passes through. The mathematics permits the possibility, but the mathematics also demands conditions that appear entirely unreachable with any foreseeable technology or energy source. The same problem afflicts warp drives. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is a fascinating mathematical object. It describes a bubble of space-time that contracts space in front of a spacecraft and expands it behind, allowing the craft to move through the galaxy without technically exceeding the local speed of light. The equations are internally consistent. They do not violate special relativity in the way a naive faster-than-light engine would. But to create an Alcubierre bubble of useful size requires exotic matter with negative mass, and initial calculations suggested the energy required would be equivalent to converting the entire mass of Jupiter directly into negative energy. More refined calculations have reduced this estimate, but every version of the calculation still demands resources and physical conditions so far beyond our reach that calling it a plan is a misuse of language. I want to be precise here because I believe precision is a form of respect. I am not telling you that these things are absolutely and forever impossible in any conceivable physical theory. I am a physicist. I know that our theories are incomplete. Quantum mechanics and general relativity are the two most successful theories in the history of science, and they are mutually inconsistent at the Planck scale. There are things we do not yet understand. A future theory, a quantum theory of gravity that nobody has yet constructed, might reveal aspects of space-time that change the picture. But here is what I want you to understand. The gap between our current physics and the physics required for practical human interstellar travel is not a gap of a few centuries of engineering. It is a gap of fundamental theory. We are not in the position of the Wright brothers, who understood the principles of flight and simply needed better materials and engines. We are in a position where the very theoretical framework we would need does not yet exist, and we have no guarantee it ever will. Now let me speak briefly about radiation. Even if you solved the energy problem entirely, which you cannot, interstellar space is not empty. It is filled with high-energy particles, cosmic rays produced by supernovae and other violent astrophysical events, traveling at near light speed themselves. At low velocities, these are a health concern over long periods. But at high relativistic velocities, from the perspective of the spacecraft, the density of these particles appears to increase enormously due to length contraction. The shielding required to protect human biology from this radiation at high fractions of light speed would be enormously massive, which once again feeds back catastrophically into the fuel requirements through the Tsiolkovsky equation. Every kilogram of shielding you add is a kilogram that must be accelerated to high speed, which requires more fuel, which requires more mass, which requires more fuel to carry that mass, which requires more mass still. The rocket equation is a trap that closes tighter the harder you try to escape it. There is also the question of micrometeorites and interstellar dust. At 1% of the speed of light, a particle the size of a grain of sand carries the kinetic energy of a small nuclear weapon. The interstellar medium is not perfectly empty. Impacts at these velocities would be catastrophic without shields of extraordinary mass, which returns us again to the equation that will not be escaped. I want now to turn to something more philosophical, because I think the deeper question is not merely whether interstellar travel is technically possible, but what the persistent belief that it is tells us about the human mind. And I say this with genuine compassion, not contempt, because I understand the impulse completely. When I was developing my theory of matter waves, when I was sitting in my brother's private laboratory surrounded by X-ray equipment and arguing with myself about the nature of the electron, I was sustained by a conviction that the universe had a deeper symmetry than anyone had yet found. That conviction turned out to be right. But it was not wishful thinking. It was guided at every step by the equations. The equations were the discipline. Without them, the intuition is just dreaming. The dream of interstellar travel is an old dream. It is In some ways, the oldest dream of exploration displaced onto the cosmos. And there is nothing wrong with dreaming, but when popular science communicators present interstellar travel as a solved problem in principle requiring only engineering, they are not being honest about the mathematics. When space agencies discuss it as a goal for the next century or two, they are not being honest about the physics. When films like Interstellar, however beautiful, however earnest, present wormholes as devices that five-dimensional beings might conveniently place near Saturn for our use, they are creating a false familiarity with ideas that remain deeply unresolved even at the theoretical level. And this dishonesty has a cost. It displaces attention and imagination from problems that are genuinely soluble. The robotic exploration of our solar system is not a consolation prize. It is extraordinary. The Mars missions, the James Webb Space Telescope revealing galaxies from the first billion years of the universe, the detection of gravitational waves from colliding black holes. These are achievements of real physics, real mathematics, real engineering. They deserve the wonder that gets redirected into fantasies about what is almost certainly impossible on any human timescale. Furthermore, the practical challenges of sustaining human civilization on this planet, which is the only planet confirmed to support human life, deserve the intellectual energy that gets poured into imagining our escape from it. When people speak of interstellar travel as humanity's insurance policy against extinction, they are using the impossibility of the venture as a kind of comfort, a mental safety net that costs nothing to imagine and requires nothing to act upon. It is the physics of procrastination. I'm not saying we should stop doing fundamental research on propulsion or general relativity or quantum gravity. Quite the opposite. These are among the most important frontiers in physics, and breakthroughs in our understanding of space-time could, in principle, reveal something we do not currently suspect. I am saying we should be honest about the current state of the mathematics. We should say clearly, with the physics we have, interstellar travel for human beings is not merely difficult. It is so far beyond our current capability as to constitute a qualitatively different category of problem from the ones we have previously solved. The equations do not lie. They never have. The de Broglie wavelength of an electron was a prediction that seemed absurd, and it was confirmed. The special relativistic mass increase was a prediction that seemed impossible to test, and it was confirmed in particle accelerators within decades. The existence of gravitational waves was predicted by Einstein in 1916 and confirmed a century later by LIGO. The mathematics, followed honestly, has never led us wrong, and the mathematics of interstellar travel, followed honestly, leads us to this. The stars are not going anywhere. They will be there in 1,000 years. They will be there in 10,000. If there is to be a civilization capable of genuine interstellar travel, whether by some undiscovered physics or by generation ships moving at a fraction of light speed across geological timescales, it will be built on a foundation of hard-won understanding, not on the assumption that Hollywood's shortcuts are waiting to be engineered. The greatest journeys in the history of physics began not with the answer, but with the willingness to follow the question wherever it led, even when it led somewhere uncomfortable. When I wrote down my hypothesis in 1924, I did not know whether matter waves were real. I only knew that the equations demanded them. I followed the equations. That is the only way forward that has ever worked. So follow the equations, all of them, especially the inconvenient ones. And when they tell you that your dream is a mathematical lie, do not look away. Look harder. Because sometimes the constraint itself is the discovery, and sometimes the discovery that one door is sealed forever is what finally forces you to find the door that was always open. Thank you.